Chapter 2, Exercise 2.87, Part A. How much energy is required to ionize a hydrogen atom containing an electron in the n equals 4 level? To ionize a hydrogen atom, you need to have n equals infinity. That means the electron and the nucleus are completely separated. So really in this question we need to calculate the energy difference between n equals 4 and n equals infinity. How do we get the energy difference? There's an equation in the book, so you can access the corresponding section in your e-textbook. But for now, I'm going to show you the equation over here. It's actually negative 2.18 times 10 to the power of negative 18 joule. Alright, that's actually the energy for n equals 1. What about the energy for n equals 2? That's going to be 2 squared. What about n equals 4? That's going to be this. Alright, this is the energy of the electron in the n equals 4 level. It's negative 1.36 times 10 to the power of negative 19 joule. Now, after this hydrogen atom is ionized, this n becomes infinity. So it goes from 4 to infinity. And once you have infinity on the bottom, or infinity squared on the bottom, well, the value of the fraction is going to be 0. So really it's going to be 0 minus this number. That's going to be the difference. So 0 minus this number, that's going to be the energy difference between n equals 4 level and n equals infinity level. We can see the answer here. It's 1.36 times 10 to the power of negative 19. So I'm gonna just enter this here, 1.36 times 10 to the power of negative 19. However, I would like to try this. I want to know if this works as well. Probably not. This works in Excel if you know how to use Excel. But over here, I don't think it works, but I will try it anyways. Alright, it's incorrect, but at least we have, this equation over here that we can use. And then I'll change the format. Press Shift 8 to get multiplication, and then 10, and then Shift 6, and then negative 19. Alright, now it's accepted. This is accepted. Over here n is infinity, here n is 4. We take the difference, we get this number. Part B. What wavelength of light contains enough energy in a single photon to ionize a hydrogen atom? Alright, so over here it does not say the original energy level, so I'm gonna assume it's 1. I'm not sure. So part B is unclear. To ionize a hydrogen atom. So in the hydrogen atom, we could have an electron in the n equals 4 level. We could have an electron in the n equals 1 level. Because this is 2 parts in the same question, I think what I will do is I will just convert the answer to part A, 1.36 times 10 to the power of negative 19 joule. I will convert this energy to the wavelengths. Now how do we do this? Well, once we have the energy here, the first step is to get the frequency. The energy of the photon divided by the Planck constant. We get the frequency of the photon. Once you have the frequency of the photon, you can then calculate the wavelength of the photon. How do you get the wavelength? Well, it's the speed of light. 3 times 10 to the power of 8 meter per second divided by frequency. Now you have the wavelengths. This is the wavelengths in meters. Let's take a look. This is the wavelengths in meters, so that's why you see a small number. Now I will convert this to nanometers. 1 meter is a billion nanometers. Alright, we have 1461 nanometers. If we need 3 stick figures, I'm gonna do 1.46 times 10 to the power of 3 nanometers. Again, I used the answer to part A over here to compute lambda here. What if this hydrogen atom has an electron in the n equals 1 level? And then in this case, I need to multiply this by 4. And then I need to divide this by 4, I believe. But let's finally take a look. The energy of the photon divided by the Planck constant, we get the frequency. And over here we have lambda. Lambda is the speed of light divided by the frequency. We get wavelengths. However, this wavelength is in meters, and then I convert meters to nanometers. Okay, let's take a look. Yeah, it's correct. Just somehow part B follows part A, so you use the energy over here, and then you do this. Lambda is hc over the energy. Alright, but what I did is I did this calculation in 2 steps. I used the energy of photon divided by h to get a frequency, and then the speed of light divided by the frequency, I got lambda. Oh, I just realized that I said something incorrectly about this. This is actually 16. So if n equals 1 in the hydrogen atom, I need to multiply this number by 16, not by 4, by 16, because it's going to be 4 squared by 16. And then I need to divide this number by 16 to get the wavelengths of the light that contains enough energy to ionize a hydrogen atom with n equals 1. Okay.